welcome to the course Advanced Reaction Engineering. So, in this course today we will discuss about collections and rate data analysis. So, there are various methods. So, today we will discuss basically the integral method of analysis and nonlinear regression methods that we will discuss. Okay. So, collections and analysis of the rate data by considering a particular constant volume batch reactor that we already have discussed in our last class. So, usually whenever we conduct any let us say liquid phase reactions in a batch reactors when there is constant volume. So, in that case when the reactions we started, so we need a specific time. So, maybe 10 minutes, 20 minutes, 30 minutes or 1 hour to complete the reaction. So, once the reactions we have started, so then at with increasing times or progress of the reactions, the concentration of the reactant gradually that will decrease. So, then for the batch reactor data whenever we are going to analyze, so then the things will get time against concentrations. So, Ca if is going C is naught is the initial concentrations and A is going to product. So, this is the reaction. So, then with increasing time the concentrations gradually decrease and product formations gradually increase. So, this data from here, so how to find minus dC by dt, that is the rate data, how to find out that we have discussed in our last class, and most of the easiest method that was discussed, that is the polynomial fits or graphical method or least square analysis numerical methods that we can use to find this rate data. So, for the liquid phase reaction. So, now we have this concentration and this rate data time with respect to different time, this data we have. So, now differential method of analysis we have discussed. So, now integral method of analysis. So, integral method of analysis usually reactions order 0 order, first order, second order or maybe n equals to any fractionals order, n equals to 2.5 like this, these are the fractions order, any order we can get. So, first one by ones 0 order, first order and second order by considering the rate equations, how to evaluate the reactions rate constants C to the power alpha. So, specific reactions rate constants and alpha how to find out, means order of the reactions and specific reaction rate or reactions rate constant we can find out at a particular fixed temperatures. So, at if temperature vary from means same reactions, we can conduct the reactions at let us say these reactions we can conduct let us say at temperature 100 degree centigrade. Similarly, the reactions we can conduct 120 degree centigrade also. Similarly, we can conduct the reactions 150 degree centigrade. If the reaction is possible 100 to 150 degree centigrade, if it is possible to achieve, then this different temperature we can achieve and we can corresponding activation energy also we can find out by getting reactions rate constant at different temperature, that we will discuss later. So, now our objective is to process this data by using integral method of analysis and then nonlinear regression techniques. Okay, so, that we will discuss. So, here's let us say this is the reactions, this is the order of reactions, rate equations minus dCA by dt equals to minus RA. So, this is the rate equations. If we consider n equals to 0, means 0 order reactions. Okay. So, 0 order reactions, then rate equations would be this. If n equals to 0, then minus R equals to minus k. So, usually minus R equals to k into C to the power n equals to 0 if we put. So, then n equals to this minus k, it is coming like this. Okay. So, now this would be this, here it would be plus. Okay. So, minus R equals to k into C to the power n, if we put n equals to 0, C to the power 0 equals to this k, or R equals to minus k, we can write this. Okay. Or minus R A equals to plus R equals to, we can put this. Okay. So, here we can write dCA by dt equals to minus k. Now, if we rearrange this equation once and integrate with respect to this boundary condition t equals to 0, C A equals to C A naught, t equals to t, C equals to C A. Okay. So, these boundary conditions if we integrate this, so you will get equation 2. So, this is for n equals to 0 or 0 order reactions. Okay. Same reactions if we consider a first order reactions. So, then we can write these equations minus R A equals to minus d C A by d t equals to C to the power n, n equals to 1 first order reactions equals to k into C A. So, equation 3 you can write this. Okay. So, now if we integrate this with respect to the boundary conditions at t equals to 0, C A equals to C A naught, at t equals to t at any time C equals to C A. Okay. So, these are the boundary condition. This way if we integrate this, so we will get from equation 3 you can get this, from equation 1 we can get equation 2. So, if it is 0 order reactions equation 2, if it is first order reactions you have to use equation 2, equation 4, and if it is second order reactions, so then we can write the rate minus dCA by dt equals to k Ch square. So, by integrating with the boundary conditions we can get equation 5. So, if it is second order reactions. Okay. So, this is number 1, n equals to 0, n equals to 1 first order reactions and n equals to second order reactions. So, these are the equations we have, and experimentally we have found T against C A. So, here if it is 0 order reactions we have these equations, and for first order reactions we have this equation, and for second order reactions we have this equation. So, in the 0 order reactions, if we consider 0 order reactions n equals to 0 or alpha equals to 0, then we know C A and T. So, if we plot C A against time, so then it would be like this dotted point will come, the lines will come slope negative. Okay. So, from here we can get that, or we can say that if the reactions is 0 orders, so if we apply integral methods, the slope would be slope equals to here equals to minus k negative. Okay. So, for 0 order reactions, and if it is first order reactions alpha equals to 1, here alpha equals to 1. So, then if we plot ln C A naught by C A against time, if we do plot, so then these dotted points we can get, and if you take a straight lines, so then it would be like this, and from the slope we can get k value. So, that we can put it here for the first order reactions. Okay. So, what are the value of k would come, C A this. So, this would be the rate for first order reactions, and if it is second order reaction, similarly we have this value 1 by C A we have to do. So, now 1 by C A against time we can do plots. So, then the plot would be like this. If we plot y axis 1 by C A and x axis time, so then this against this we are plotting. So, then these dotted lines dotted points we can get for the second order reactions alpha equals to 2, that is the second order reactions. So, then we can get slope and intercept also we can get. So, once we know the intercept, that would be the value 1 by C A naught equal to that value. So, from here C A naught we can get, and from the slope we can get k value. So, if it is the second order, so then it would be straight line, and if it is not second order, not following the second order, then 1 by C A against time if we do plots, the dotted lines would be like this and lines would be not straight lines, it would be like this. If this is not acceptable, so alpha not equals to 2, it means the order of the reactions is not second order. So, when alpha equals to 2, then the lines would be straight line. Okay. So, then that data would be acceptable, otherwise this data is not acceptable. So, means the order of the reactions for these reactions we have considered, let us say second order, that is not fitted well. So, proposed reactions order did not fit with the data. So, then the reactions is not second order. So, in this case, okay. But if it is fitted like this way, then we can accept, and we can say that the reactions orders we have considered alpha equals to 2 fitted wells, and we are getting that, then we can say it is a second order reactions, or alpha equals to 2 or n equals to 2 second order reactions. So, now nonlinear regressions means this is the differential method, integral method of analysis that we have discussed. Now, nonlinear regression technique, that is computational technique. So, that we can use for the searching of parameters. So, here these three specific order of the reactions, let us say that is the n equals to 0 order, n equals to 1 first order, n equals to second order. These three cases we have discussed, but in some cases we can say that the order of the reactions not exactly 1, it may be 1.1 or it may not be 2, it may be 1.7 order of the reactions. So, then how that we can find out? So, for that nonlinear regression techniques we have to use. So, to find out that data. So, directly we can find out. So, we have to apply nonlinear and least square analysis for the analysis. So, here let us say a number of experiments we can do to evaluate those parameters. So, here the parameters for the rate equations equals to so k and alpha, k value and alpha value we have to find out. Here from the experiment these are the data points are given, means concentrations and rate data given, these data and this data are given or given, these data also evaluated or given. So, only these are two unknown. These two are unknowns, we have to evaluate by using nonlinear regression techniques. Okay. So, here to find the parameter value, so we need this rate, these are the experimental rate. So, here the rate whatever we are getting from the experimentally observed data points. Okay. These are the data points are experimentally based on the concentrations we have by using polynomial fit or whatever we have evaluated this data. So, we are getting from experiments, and this rate this is the our proposed reactions rate equations. Okay. So, from the experiment rate data value, the data points we know, but these rate equations that we do not know, this is our proposed means theoretical rate equations. So, in theoretical rate equation these are the two unknowns parameters, what would be that value if this rate equation fitted well with the experimental data. Okay. So, here what we have to do means minus RA experimentally we can find out from here, these data points we can put. Okay. And see here we have to choose alpha and k value such that let us say alpha value 1.8 we are choosing, k value 0.002 we are choosing. This is just guess value, that may not be true, but we are guessing that order may be 1.8 order and reaction rate constant may be this. So, these are two knowns. Now, Ca value experimentally we have evaluated Ca value, this value from the experiment we have conducted. So, now this Ca value if we put it here, corresponding rate we can get. So, rate calculated value, this was experimentally we have evaluated. Now, by putting that corresponding value we can get this rate value. Similarly, these concentrations we put, this corresponding rate we can evaluate. This way we can do the calculations, means we can all data points we can calculate by using our proposed rate equations. So, if this rate experimentally rate and this calculated rate both are almost close to that value. So, let us say here experimentally rate we are getting 0.02 and calculated rate is at this particular time, let us say 300 minutes we are getting 0.019. Okay. So, these two value almost close to each other. So, then we can say that it is fitted well. If here this is experimental value and calculated value that we are getting 0.002. So, these are two different, not same value. So, then it is not acceptable, means the guess, initial guess whatever we have guessed, that is wrong. So, some different value we have to choose. So, here this is the sigma square, that is we have to, this quantity sigma is a square by n minus k. A square is the sum square of this rate measure value or experimental value, and this is measured value from this equations, and this rate is experimentally value. So, sum of these squares for all data points, this data point, this difference, this data points, these two rate difference, this is R A experimentally minus R A calculated. This difference, these data points if you take and sum of those value and divided by n minus k, n is the number of runs, let us say totals 20 runs we have done, and number of parameters to be determines 2 parameters alpha and k. So, 20 minus 2, we can a square value we can put it here. So, then if we sum up those things, so this sigma square value we have to know, okay, sum square value. So, RIM, that is the measured reactions rate, RI means calculated reactions rate from the rate equations, C to the power alpha. So, from this rate we have to find out, and this is experimentally we have find out already by temperature concentration data we have evaluated this. So, this data we have evaluated, this is experimental data we have evaluated. So, now calculated data we have. So, this way we can find out. So, but here the sigma square value is very important. Sigma square value that depends directly on the value of alpha and k value, the value we are putting in the rate equations. So, initial guess whatever we have guessed value 1.8 and k value let us say 0.02 we have guessed. So, maybe this may not be, this guess is perfect or correct. So, if this value whatever we have here, it is given alpha and k value, let us say alpha equals to 2, k equals to 5, and we have substituted here alpha and k value in these equations, and experimental or calculated k we have find out, experimental rate is given. So, the sum square sigma square value, this is k value x axis and this is z axis alpha, y axis sigma square. So, by putting these two we are getting sigma square value let us say 57, that is very large value we are getting. Then the whatever initial guess we have taken for this, that is not acceptable. As against another guess alpha and k value, another point data point alpha equals to let us say 1.5 and k value let us say 0.3 we are guessing. Based on that, say again sigma square value we have to find out. So, there also we can see that it is also very, it is coming very large value, against this guess is also not acceptable. So, like that another guess also we have to consider. So, by that way it is coming sigma square value is coming very close to 0. See the changes of the sigma square value is 57 to 0.045 sigma square minimum. So, then this value would be acceptable. Okay. So, then whatever for this let us say we are guessing alpha equals to 1.8 and k value is 0.00003. So, then only this value is acceptable, rest of the values are not acceptable. By that way we can find out the value of this sigma square. Okay. So, by that way the minimum value, the minimum sum square value sigma square, one can use the optimized techniques or the any software package, means this initial guess alpha and k value means what we will choose, that is very important. So, by theoretically this so many trials you have to do to find out this sigma square value this. So, for that so many software packages there, softwares we can use, there's many iterations will be there automatically. So, we do not have to put any value. So, 0 to 10 for n, 0 to any 10 to the minus 10, any value in number of points, both will be means provided automatically by default. So, then sigma square value would be close to 0.00003. So, then that would be acceptable. So, then reaction means runs will be stopped and corresponding alpha and k value we can get for this particular reactions. Okay. So, by that way we can use means or evaluates or we can means approximates the order of the reactions or reactions rate constant or specific reactions rate for any rate equations. So, we can evaluate. Okay. So, here one numerical problem we are just discussing how the system does work. We have the concentration time data, that is experimentally obtained data, and this is the rate equations let us say. So, here if we do integrate this these equations after rearrange means dCA by Ca to the power alpha minus k into dt after rearranging these equations, and then if we do integrate. So, then we can get these equations. Okay. So, once we get these equations, so then after that Ca whatever that is the final concentrations, we are putting it at the left hand side and right hand side with respect to the times we are putting. So, now using polymaths or MATLAB softwares we can find out what would be the alpha and what would be the k value. Ca naught is known, okay, that is known. Initially how much concentration of the reactant that was taken to conduct the reactions, that is known. That is once it is known. So, then this value by using polymath software, MATLAB softwares or any other software, this is nonlinear regression techniques we can use to minimize the sum square of the difference in between the measured and calculated concentration data by using n data points. Okay. So, now A squares we have to find out. Ca this is the experimental measures, this is Ca calculated, this Ca calculated from here. So, n number of alpha and k value we can put it here. So, then Ca value will get what would be the calculated value would be here, and experimentally measured value the concentration at that particular time is known, the difference will come. So, here this is the measured experimentally and this is calculated value, both will be put here, and then we have to take square. Okay. So, then by that way all data points you have to be a number of data points you have collected from the experiment. So, a number of data points from the calculations we have to evaluate, and then the difference sum square we have to put it here. So, by this way we can evaluate a square value. Okay. So, otherwise here we have used concentrations, we can express that this equation in terms of time also. So, if we express time, calculated time, right hand side we are putting concentration, left hand side we are putting times. Earlier one it was left hand side we have put concentration, right hand side that was the time. So, if we put different concentration, since we have T and Ca value, Ca naught is known. So, this value we have put it, now we will put this here, and then corresponding Ca naught is known, so alpha k value that guess Tc value we can get, calculated T and this is experimentally T. So, measured experimental T and calculated T both we can put it like this way, then sum square A square value we can get in terms of time. Okay. Then corresponding alpha and k value we can get, okay, evaluate either this way or this way concentrations we have used concentrations data, and that way here time was used. Okay. So, both are the same things, but the two different parameters experimentally we obtains, one is the time, another one is the concentrations. So, either way we can feed the experimental data with the theoretically evaluated data by considering say particular rate equations and guessing order and specific reactions rate for that reactions. Okay. So, both the way we can evaluate our rate data whatever experimentally we obtains, and by that way we can get a very fitted well fitted with the experimental results a rate equations, that is minus R A equals to k into Ca to the power alpha. So, here maybe if it is fitted very well Ca to the power 1.18. So, this will be the rate equations for our means after A square, or that is very close to this way acceptable or sigma square very close to. Okay, so this way we can say that rate constants and order is this usually is called power law models. Power law models. This type of models are fitted of the rate equations is called power law models. Okay, thank you. I think it is clear to everyone. So, thank you.